All right, so yesterday we talked about the idea of a confidence interval, and we're just going to build on that today. So you already know what a confidence interval is. You already know how to interpret what it means. But we're going to talk about actually building them today. Like, how do you actually create one? So again, your confidence interval is all based on your particular sample p hat, and your p hat is particular to one particular sample. So if all of you guys did the same thing, same experiment, whatever, you guys would all probably have different samples. So you have all different p hats, so you have all different confidence intervals. Yesterday, we kept talking about just generically 95%, and talking about the 68, 95, 99.7 rule, and so that 95% was 2 standard deviations away from the mean. And so we used 2 generally as how many standard errors. That's not correct. That's just a good way to start explaining things. In fact, we use critical values. So the number of standard errors that you would use is called a critical value. That's all it means. Critical values you're going to find in your calculator, right? We talked about 95% confidence a lot yesterday, but you can choose whatever confidence level you want, and with each confidence level comes a different critical value. So a critical value is going to be denoted by a Z with a star because it comes from the normal model, but it's not an actual Z score. So we can't just say Z. It's not a Z score, but it's coming from that idea. Okay? Someone give me some random confidence percentage. Don't give me 68, 95, or 99.7. 92, perfect. So using that idea from yesterday, that the 95% confidence covered that middle 95% of your sample distribution model, we're going to use that same idea. For 92% confidence, we want that middle 92%, right, around our mean, to hopefully trap the true proportion P. Well, the critical value is the actual score that comes from the normal model with a mean of 0 and a standard deviation of 1. Okay? I need to know what those numbers are. You have to have your critical value to know how many standard errors you're going to use in this formula I'm going to show you in a second. So we use inverse norm, right? If we know a percentage, we can generally find these numbers on the number line part with inverse norm. So this is how you think about that. We want the middle 92%, so what percent is left over? And there's 2 halves, so what percent is on each half? So there's 4% available over here and 4% available over here. So if I'm looking for this particular Z value, then I use inverse norm, and the area is just 0.04, right? We did that back in chapter 6. We've done inverse norm a few times lately in other chapters as well. So we go to inverse norm. We're using an area of 0.04. It reads from left to right. The mean is 0 and standard deviation is 1. You're not putting in your p hat and your standard error there. Critical values are coming from this standard normal model. Okay? So I have negative 1.75. You can do it again if you want to, but that also means the one on the right-hand side is positive 1.75. Right? So the critical value that you use is, because we talked about yesterday, we have plus and minus from on your mean, right? So we'd have negative 1.75 and 1.75 times the standard error. Okay? Yesterday, using this idea, we talked about 95% a lot. Well, if we have 95%, yesterday we used 2 standard errors. It's not technically 2, or it could be more precise than that. All right? So if you have 95% confidence, what percentage is left over for each side? 2.5. So if I do that in the calculator, I get a critical value of negative 1.96. This would be positive 1.96, right? If you don't want to look that one up all the time, I would commit it to memory. We talk about 95% confidence over and over and over again. All right, so we have a critical value of 1.96, not 2, like we talked about yesterday. It's not a big deal. We just can be more precise. If you forget, then this is how you would do it. I would suggest drawing a little picture, putting your percentage in the middle to figure out how much is left over on each side, and then using inverse norm to figure out what your critical value is going to be. You only have to find the one on the left because the one on the right is going to be the exact opposite, it's positive, right? So that's how you're going to find your critical values. What you need to know, again, when I give you the actual appropriate formula for building a confidence interval in a second. Okay? Does that make sense to everyone? Okay. When you're building a confidence interval, just like when we had a sampling distribution model, which our confidence interval is based on, we have to check conditions. Since it's based on a sampling distribution model, guess what? The conditions are the exact same. That does not mean you just don't have to check them, though. You always have to check them anytime you build a confidence interval. So you have independence. Hopefully, your data is independent. And to back up independence, you check to see if it's random, and you check to see if there's less than 10% of the population. We've already done that like a million times in the last chapter, right? Now, what's going to happen is, especially problems in the book, they're going to ask you to check the conditions. A lot of the time, if you're going to miss something in independence, it's not necessarily going to be random. For example, if it says and it tells you that the data comes from a survey that involved like a website log-on situation vote thing, is that random? Is that a random sample? What do you know about web surveys? They're biased, right? They do not produce a simple random sample, right? They aren't random. People with strong opinions go and take the survey. So in that case, it wouldn't be random. You couldn't do the confidence interval. It didn't meet one of the conditions. Okay? That's why you check the conditions. If they aren't met, you can't do it. Besides independence, you also have sample size. Since we're talking about proportions specifically in this chapter, then you have success failure. We've done these before. These aren't new. If you don't check them, you won't get full credit on an AP exam, on a quiz, or on a test. It shouldn't have to ask you to do them. If it says to construct a confidence interval, guess what? You're checking the conditions. Okay? Yes? Okay. So, here is the sum up of how you're going to build your confidence interval. We talked about the name yesterday. We're dealing with one sample, so it's one proportion. It's based on a normal model, so it's a z, and it's an interval. We got that. No big deal. Here is the formula for that. P hat, your sample proportion, since that's what it's based on, plus or minus z star, your critical value, we just talked about how to find those, times the standard error, which we talked about yesterday, which is an estimate of your standard deviation. Right? That's as easy as it is. You are going to be given p hat and n, so you can find all of this, and you build your interval. Now, on your AP formula sheet, I said this yesterday. It doesn't say on here standard error. But you should know that the standard error is the standard deviation equation when you have one proportion. It's just an estimate, so you use p hat instead of p. We talked about it yesterday. We're good with that. For confidence intervals, though, I said yesterday we're going to talk about multiple different types of confidence intervals. Depends on what kind of data you have. For confidence intervals, it does not list out all the formulas for confidence intervals on here. It does give you the format that it should be in, because every single confidence interval has the same format, but that means different little pieces that you stick in. So this is what it says on your formula sheet. It says confidence interval. It says statistic. In this case, what's our statistic? What do we have? What's this all based on? a proportion, our sample proportion, p hat. Plus or minus critical value. In this case, we're talking about z critical values, so times the standard deviation of the statistic. Well, since we're talking about a sample proportion p hat, then the best we can do is find the standard error, the estimate for the standard deviation. Best we can do. When we talk about means, it's going to be almost the exact same thing. What do you think your statistic is when we do means instead of proportions? X bar, it's going to be a mean, right? Your critical values are going to be calculated the same way. It's just going to be a different model. It won't be normal anymore. We'll have a different model, but you calculate them similar. You use a different function in your calculator. It'll be a t value. And then we'll have a standard error as an estimate for your mean. Okay? What is written in the black ink? That is exactly how it's listed on the top of your AP formula sheet. It is in words. You need to know what those words mean so you know what to put there. Okay? All right. So I'm going to do two questions first. We're just making sure we understand the conditions and we understand what the sentence is, how we're interpreting confidence intervals still from yesterday. Then I'll go into actually building a confidence interval. It's not that hard. Obviously, you follow the formula. The problem is it's not just that easy. You have to list the conditions, name the interval you're using, write the actual interval, and then interpret that interval. So on your homework assignments, on your quizzes, I should not just see 25% to 37%. That will get you 0 credit. I need to see conditions checked. I need to see the name of what you're doing. I need to see the actual interval and where it all came from. And then I'll need to see what that interval means. Right? That's your job, to do all of those things. All right, we're only going to do the first two of these. All we're doing, though, is following the directions. We're not actually calculating any intervals. So it says, for each situation described below, identify the population and the sample. That means you need to tell me what the population is and what the sample is. Explain what P and P hat represent. So what is P and what is P hat? And tell whether the methods of this chapter can be used to create a confidence interval. That means check the conditions. If the conditions are met, then yeah, we can do a confidence interval. If not, no, we can't. That's what I asked you to do, so I expect you to do all of those things. So, for A, police set up an auto checkpoint at which drivers are stopped and their cars inspected for safety problems. They find that 14 of the 134 cars stopped have at least one safety violation. They want to estimate the percentage of all cars that may be unsafe. So what is the population I'm referring to? All cars. What's our sample? The cars that were in the sample, so the 134 cars. So what does P represent? We don't know P, but what does P represent? The proportion of unsafe cars. And then what does P hat represent? Right, proportion of unsafe in my sample. Okay, last chapter, they were telling you specifically, they would say, whatever this percentage is, they would say this percent of all cars. And it wasn't necessarily they were using P as like, they were giving that information. They were telling you, here's what P is. That's the way you could learn what a sampling distribution model is. That way you could build a model based on your sample size to see if things were unusual or not. The problem is, practically, hardly ever do you actually know P. Like, it's easy to figure out for M&Ms, right? There's a ratio that the company figures out, and that's what it's based on. It's impractical to go and find the percentage of diseased C fans. Right? It's never going to happen. It's never going to happen that I'm going to be able to survey every single car in the entire world to figure out how many are unsafe. Okay? That's a good question. Everyone good so far on those 4 things? So I'm not going to write all the conditions out, but we are going to check them. So independence. Are the cars independent? They should be. Since we're checking unsafeness, or whatever you want to call it, there shouldn't be any reason that one car that's unsafe should influence another car that's unsafe. Or not unsafe, whichever. So to back that up, for randomness, are these cars random? Does it say they're random? Doesn't say they're random. Can we assume they're a good representation of all cars? I'm going to. There's 134 of them, and it doesn't really say that they're in any specific kind of place that would only have like vans or anything, right? So I'm going to say they're a good representation of the population of all cars. Is 134 cars less than 10% of all cars? Definitely. That's not a problem at all. Then for sample size, I needed to use success failure. Right now, I don't have a p-hat because they don't give it to me, but they do give me the information to find p-hat. How do you find p-hat? Right. P-hat's just a sample proportion. So a proportion is just a percentage. So 14 divided by 134 is 10.5%. So I would need to check success failure. What is N? 134. So I would do 134 times 0.105, and then I would do 134 times the complement, right? Both of those end up being greater than 10. You get 13.9 and 120.1. So it works out. So since I've checked all the conditions, it just says, tell whether you can do a confidence interval or not. So yes, I just said, and I quote, a 1 proportion Z interval could be used for the proportion of cars with safety issues. You can use one. It doesn't ask you to find one, just you could use one. Could you find one? Sure. But you don't have to. Does that make sense on part A? On part B, it says a TV talk show asks viewers to register their opinions on prayer in schools by logging onto a website. Of the 602 people who voted, 488 favored prayer in schools. We want to estimate the level of support among the general public. So who's the population? The general public. Who's in our sample? The 602 people that responded. What does P represent? Of people in favor of prayer in schools, right? What is your p-hat going to be? Right, the portion of people in the sample. That favor prayer in school. Then we check the conditions. Are these people random? No, it's coming from a biased survey. It's not a random sample. Guess what? If we missed the first condition, we can't do an interval. You don't check all the other conditions. If you miss one, you're finished. So, I said, there's no need to check the other conditions. A 1 proportion interval cannot be used. Because it doesn't meet the random condition. It's not like you have to hit 2 out of 3. It's like you have to hit all of them. It's not a random sample. It's a biased survey. All right, so this is pulling in stuff that we've learned all throughout the year. Questions on 3. I'm not doing the rest of it. Okay, making sure you understand the vocabulary, making sure you understand the conditions. All right. On number 9, still talking about cars. What fraction of cars is made in Japan? That's their question. The computer output below summarizes the results of a random sample of 50 autos. I don't know, I can't say cars. Explain carefully what it tells you. It wants you to interpret the interval. So to interpret the interval, you need an interval, got that, and a level of confidence. So how can I interpret this interval? What should I say? This goes back to what we talked about yesterday. What should I say? I am 90% confident that the true proportion of cars made by Japan is between 29.9% and 47%. I've interpreted the interval. All it asks you to do. You have to have a confidence level. You have to have an interval. The whole entire point of the interval is to try to trap P because we don't know it. Questions about that? All right, then let's talk about 11 and 12, about contaminated chicken. We'll actually do a confidence interval. All right. In January 2007, Consumer Reports published their study of bacterial contamination of chicken sold in the United States. They purchased 525 broiler chickens from various kinds of food stores in 23 states and tested them for types of bacteria that cause foodborne illnesses. Laboratory results indicated that 83% of these chickens were infected with Campylobacter. Part A says, construct a 95% confidence interval. If you're going to construct a confidence interval, what's the first thing you should do? Check the conditions. So we're going to check the conditions. Independent. Should the chickens be independent? Yeah. The chicken should be independent because why? Because you check the randomization condition. Are these random? Why? Yes. They're random because they come from various stores and states. So that should make it a good representation, right? Okay. You also know they're independent because 525 should probably be less than 10% of chicken. We eat a lot of chicken. Would you agree? Okay. Is the sample size large enough? How do we know? There should be more than 10 of it each. It's a proportion, so you should do success, failure. So N is 525, right? What's our P, or our P hat in this case? 0.83. So 0.83 times 525, and then 0.17 times 525 are hopefully both greater than or equal to 10. And they end up being, I don't recall, here, I'll just check them real fast. It probably does. 0.83 times 525 is 435.75, so that gives us plenty of room for failures, right? Okay. So you would find those numbers, no big deal. I checked my conditions. Everything seems good, so I can actually do the interval. All right. So for the interval, construct a 95% confidence interval. So here's your formula. P hat plus or minus your Z critical value times the standard error of P hat. Well, what's P hat? 0.83. What's our Z critical value for 95% confidence?
Oh,
1.96. If you didn't remember, you would think that little model. We went the middle 95%, so that means there's 5% left over and 2.5 on each side, and you would use inverse norm to figure out one of those pieces, and it would have been 1.96, right? Okay. So if you don't remember, you can still figure it out. And in the standard error of p hat, we actually need to figure out, we gotta do some math. So we have p hat times q hat divided by n .83 times 0.17, 525, that's not 525. And I can't type in this calculator, obviously. So 0.016. I'm going to multiply this up here by 0.016. So I get 0.83 plus or minus, from my calculations before, I got 0.0321. Now yesterday we talked about this. This is probably going to come up on your homework, so I'm going to make sure I say it now. That 0.0321 has a special name. The 0.0321 was where I multiplied the 1.96 by 0.016. What is the special name for the 0.0321? That is the margin of error. That is not the same thing as the standard error, is it? The standard error is just that part, right? Not the same thing. The margin of error includes how many critical values were on each side, right? So it contributes to the confidence level. All right. So if we do our plus minus, because we actually want an actual interval, we'll get an interval from, I got 0.7979 to 0.8621. That's my interval. So the math in this is not that hard. This chapter probably really won't be that hard. What's going to be hard is when I start giving you more confidence intervals, and you got to make sure you do the right one. Right? There's only one type in this chapter. You're going to be fine. I'm saying this chapter is going to be fine. But when we get to chapter 22 and I give you a new confidence interval, well, then it's going to be two different proportions. So it's going to be, okay, I just going to make sure if it's one proportion I do this and two proportions I do this. But then past this unit, we'll get into means and differences in means. So there's, I think, 4 different types you're going to have to keep up with. Again, they all follow the same pattern. So it's not like crazy different. Just to remember what statistic goes with what your data involves. Okay? Anyway, everyone go with part A. That's what we did. We constructed the confidence interval. We checked the conditions to the interval. We good? And part B. Explain what your confidence interval says about the chicken sold in the United States. That means interpret your interval. What do those numbers mean? So you're going to write a sentence, and that's going to be fantastic. What is it going to say? I am 95% confident. I'm always going to write the true proportion P just so I make sure I don't mess it up. Of infected chickens. So we're talking about infected chickens. This is important. Why is saying infected chickens important? Context. And we're always bad with context. So I'm 95% confident that the true proportion P of infected chickens is between, or lies within, or falls between, whatever, some phrase indicating between 79.7% and 86.2%. There you go. Interpreted the interval, explained what it said. Yeah? If I wanted to make it better, I could say that the true proportion of infected chickens sold in the United States, but I got the infected chicken. I just took my interval and changed it into percentages. I took the 0.83 and added the margin of error and subtracted the margin of error. Okay, questions about where that came from? All right, then let's talk about part C. This will make you think about some things with confidence intervals. A spokesperson for the U.S. Department of Agriculture dismissed the Consumer Reports finding saying that that's 500 samples out of 9 billion chickens slaughtered a year. With the small numbers they tested, I don't know that one would want to change one's buying habits. Is this criticism valid? Let's think about this. If your sample size, if you have a different sample, right? Any other sample, you make a new confidence interval, right? There's going to be a million different confidence intervals. But we are 95% confident that P lies in this interval, right? If you do a different sample size or anything, I'm still going back to that. I'm 95% confident that it's in this interval. That's only a 5% chance that it's not in this interval, right? So I don't really think it matters what the sample size is, or if you do a new sample or whatever you want to do, I'm pretty sure it's in this interval, right? So I'm pretty sure that there's lots of chickens infected. Does that make sense? So it shouldn't matter what your sample size is. It shouldn't matter if you do a new sample. I'm still this much confident about this particular interval. Does that make sense? Yes? Okay. I'm not going to do number 12. It's the same thing. It says there's more chicken. The chicken is also infected with salmonella. But it's only 15%. So apparently we're not supposed to buy broiler chickens because they're all infected with stuff. So it says, are the conditions met? We already checked all the conditions. What's the only condition that's going to change? The success failure, right? Because we have a different p hat. So that would change. It's met. And then it says construct a 95% confidence interval. It's almost the exact same thing. The standard error will be different and our p hat are different, so it'll be a little bit different, but this process is the exact same, right? So I'm not going to do it again. We good with that? Yes? Okay, then I just want to make a note. On 15, I'm not actually going to go through and do it. Again, I'm pretty sure you guys can follow that formula and construct the confidence interval. Am I right? I think so too. So let's talk about this real fast so we can talk about what it says in part B. It says the Paralyzed Veterans of America is a philanthropic organization that relies on contributions. They send free mailing labels and greeting cards to potential donors on their list and ask for a voluntary contribution. To test a new campaign, they recently sent letters to a random sample of 100,000 potential donors and received 4,781 donations. It says to give a 95% confidence interval for the true proportion of their entire mailing list who may donate. I did that, and I got 4.65% to 4.91%. That's a very small interval, but I'm still 95% confident, right? So it's not like I made it more precise by making myself less confident. It just ends up being rather precise, okay? On part B, it says a staff member thinks that the true rate is 5%. Given the confidence interval you found, do you find that percentage plausible? Here's what I would say. I'm 95% confident that P is in my interval of 4.65% to 4.9%. 5% is plausible, though, right? 5% is 0.1% more, right? So it's not like it's 20% more. So it's plausible, but I doubt that it's actually going to occur since I'm 95% confident about this interval. It's plausible. If they had said like they think it's 10%, I would say that's not plausible. I'm 95% confident it's in this interval, right? 5 being so close though, you gotta be kind of wishy-washy. Like, yeah, it's really kind of close. So it's definitely a possibility. There's that 5% of non-confidence, right? But I'm rather confident about my interval. But this is only one sample, so who knows? I was feeling good about doing confidence intervals based on sample proportions. All right, well, I'm going to give you the assignment.